So our first speaker will be Dr. Cor-Paul. So he is currently an associate professor in software engineering in electronic engineering and computer engineering department at University of Alberta. So he is the Canada's research chair in quality assurance of intelligent systems. He has the analytics software G Games and the repository data lab, and is one of the vice chairs of the SPEC Research Group on DevOps Performance. So his research interests cover quite a wide variety of software engineering, performance engineering related topics, including, for example, automated testing, quality assurance, empirical software engineering, and mining software. So he won the University of Alberta Faculty Engineering Early Career Research Award and a SPEC Contributor Award in 2022, and has published many top-tier software engineering conferences. So welcome.
Thank you very much, Leigh, for the introduction. So hi, everybody. My name is Cor-Paul. Today I'm going to talk to you about visual software quality assurance using foundation models. So my talk will be a bit different than all the other talks. So you saw lots of great talks on that have to do with code. So you will not see a single code snippet in my presentation today. So I had the ASGAARD lab. ASGAARD stands for Analytics of Software Games and Repository Data. And we study how foundation models can help us with visual quality assurance. So if you're interested in our work, check out our website. All our papers are there. So the work I discussed today is based on the work of these amazing students. So Mohamed Reza Taiziri, Finlay Macklon, Chunjun Feng, Marcus Figiato. Mohamed Reza and Finlay are graduating soon. So if you're looking for great PhD students to join your company, feel free to reach out to them. So what is visual quality assurance? So visual quality assurance is basically the process of ensuring that there are no visual bugs in your software. And visual bugs are bugs that express themselves visually. And what does this mean? You can basically detect them by just looking at what's happening on the screen. Okay, so the interesting thing is that these bugs are typically very easy to spot for a human, but very difficult to spot for a computer. So as a result, a lot of this type of testing is done manually, which is of course very expensive and very tedious. So to give you an example of what we're talking about when we talk about visual bugs, you can think about GUI related issues. Okay, so here in the menu, you see that there's some overlap. I'm sure that you have used a website at some point where the menu functioned like this, and it's very annoying to work with. So another example is this, where a checkbox in a form is broken and you cannot actually use it. Okay, so these are very well-known examples of visual bugs. But there are lots of other types. So here's an example where the person on the right isn't as beautiful as they're supposed to be, because a texture is missing from the face. Okay, so when you talk about different kinds of software, different types of visual bugs can occur. So this is an example from the game industry. So why do these bugs matter? You might just think it's just visual, we can just look through it. Well, the way that software looks is the first thing that end users encounter. Okay? And a poor visual experience can ruin the overall user experience. So this is a huge problem. And even worse, like you saw, some of the bugs can even render the software unusable. Okay, so think about the GUI bugs. If you cannot use the software, it's basically worthless. Okay, so just a side note that almost all the examples in my talk come from games. This is because games contain a lot of very hard to detect visual bugs. And most of the testing for games is still done manually. Okay, so they can benefit the most from the type of work that we do. Also, they're a lot of fun to work with, right? Okay, so I would like you to place yourself in the role of a game tester and see if you can spot the bugs on the next slide. Because some visual bugs are hard to detect even for humans. Okay, so this one, can I see some hands who sees it? Okay, so here there's a placeholder texture on the tablecloth and the table. Okay, so this ended up in production somewhere. This is another example. I see some hands who sees it? No, it's just very difficult. So I know that this soccer team is not very good, so they play a very strange type of soccer. But the position of the leg is very unnatural. Okay. And the final one, this is a very difficult one. So it's actually raining inside. Okay. So these type of bugs, they're extremely difficult to detect for a human already, but even more so for a computer, because how do you specify a test oracle for these type of bugs, right? There are so many things that can go wrong, especially when they have to do with the physics engine of the game. You cannot really specify a test oracle for that. So they require common sense reasoning, okay? So as a human, we know that it's not supposed to rain inside a building, but what about an AI model? So we set out to study whether foundation models can actually help us to detect bugs in video game screenshots, because that's the data that we have available, okay? And if you play a lot of games, you may recognize this type of bug. It's the bucket head glitch, which is a glitch in Skyrim, where you can put a bucket on somebody's head and they cannot get it off, so they have to play with the bucket on their head. But let's take a little bit of a simpler example, right? Let's go back to our placeholder texture bug. So what does a foundation model need to describe, to understand, to detect and to describe this bug? So first of all, it needs to identify the table, okay? Then it needs to identify the tablecloth. And then it needs to be able to reason about what they normally should look like. Okay, so this is a very, very difficult problem. Well, as it turns out, if you give this image to GPT-4v, so GPT-4v is the vision version of GPT-4, which can actually take images as input. So if you give this image to GPT-4v and you ask it what is wrong with this image, it actually gives you a very good response. Okay, so it basically describes what's happening in the image, and I'm not going to read the whole thing to you, but it's super impressive what happens. And in the highlighted part, you can see this could be a glitch or a placeholder graphic that was not replaced with the final texture in the game's development. So it's amazing that a model out of the box can give us this type of information without any fine-tuning or training or whatsoever, right? So this is really, really promising. So we wanted to know more about how well foundation models can do this already for us. So we created a benchmark to evaluate the bug detection capabilities of LLMs, so large multimodal models. And we call this GlitchBench. So GlitchBench consists of 593 images and descriptions of video game glitches from 205 games. Okay, so the paper got accepted a few weeks ago at CVPR 2024. So it's already on the website if you want to read the preprint. Have a look at the website if you want to access the data as well. So this is really interesting data to work with because there's no benchmark that's anything like this, okay? So what we did was we used the data in GlitchBench to evaluate the bug detection capabilities of 11 foundation models. So we looked at one commercial model, clearly GPT-4, and 10 open source models like Lava, QN, Blip, and 7 other ones. And we asked it 3 questions about the data in GlitchBench. Okay, so the first question is what is unusual about this image? The second question is what is wrong with this image? And the third question or task was to describe the image in detail. So the idea is that the first 2 questions give us an idea of the bug detection capabilities. And the third task actually helped us to understand why the model got something wrong for the first 2 questions, okay? Because we wanted to see if it was able to spot all the objects in the image, wanted to see if it was able to understand certain weird things in the image, and so on. So we took the data from the GlitchBench and for every image in the data set, we asked these 3 tasks. And then what we did, we used a language model as a judge. So we used Llama 2 to judge whether the response of the foundation model and our ground truth were semantically similar. So we had a short ground truth text that described what was wrong with an image or what was the bug. And then you can imagine that a foundation model gives you free format text, right? So it's actually quite tricky to compare these two, and we didn't want to do this by hand. But you can use a model as a judge to basically ask whether 2 texts are semantically the same. And modern models are really good at this because it's just simple text analysis, right? So we got all the responses from the foundation models, and then we took that together with the ground truth for the images, and we fed that into the Llama model, and the Llama model would just tell us, yes, this is similar, or no, this is not similar. And that's basically how we computed the accuracy, okay? So what we learned is that current foundation models can already do a quite reasonable job at bug detection for video games. So GPT-4v has an average accuracy of 43.4% on the data. Okay, so the average accuracy is the average accuracy over that first and second question that we asked it. But the interesting thing was there was actually a large gap between Q1 and Q2. So for the first question, it achieved an accuracy of 57.2%, and for the second one, it achieved 29.5%. So we did not initially expect that a small change in the prompt would affect the overall accuracy so much. So this is another example of how important this prompt tuning is, right? Another interesting observation was that it was actually really good at seeing that nothing was wrong with glitch-free images. So we also did a control run with about 300 glitch-free images, and we asked it what is wrong. And basically the answer should be nothing is wrong. And it could do that in almost 92% of the cases. Okay, so it's relatively reliable for that. So another interesting thing was that Lava was the best performing open source model, not totally unexpectedly. And it achieved an average accuracy of 35.5%, but there was not such a big difference between the two different prompts. Okay, so the average accuracy was close to GPT, but if you look at the separate prompts, then it was quite far off. Okay, so we looked further in the cases that it could not detect correctly. And we saw that GPT-4v can actually see details in images quite well, but it cannot always focus on the unusual aspects. So what we saw, for example, in the Batman, the rain inside example, is that it was actually focusing on the color of Batman's suit, which is red in that image because of some lighting aspect, okay? So we saw that GPT-4 could explain the images in almost 65% of the cases. So for most of the images, it actually understood quite well what was happening and which objects was there, and so on. But it can only correctly detect the bugs in 57.2% of the images. So there's still a bit of a gap there in the reasoning capabilities. Okay, so another very promising observation for us was that Lava 1.5, so the open source model, actually outperformed GPT-4 in one of the bug categories. So we had 4 or 5 bug categories. I don't remember all of them, so have a look at the paper if you want to know which ones. But in the rendering and texture bug category, Lava actually outperformed GPT-4. So why is this interesting? Well, this category is actually the most occurring bug in the game industry from our experience. Okay, so most game developers actually have to deal with many of these type of bugs. So it's very promising that an open source model is good at detecting those bugs compared to GPT-4, because then you can actually work with it, right? It's cheaper, you can fine-tune it if you want, and so on. So you're not really tied to having to use that expensive GPT-4 interface. So one thing that I have to say though, we think that it may have to do with some privacy features of GPT-4, because if you look at this, then the problem is in the face, right? So the texture is missing in the face, and GPT-4 is not that good at recognizing and analyzing faces because of some privacy features. So it could be an aspect of our data. Okay, so glitchbench is a lot more difficult than existing benchmarks. So we looked at how the relation was, or the ranking of the models that we tested in other well-known benchmarks. And there, all the models were able to achieve like 80–90% accuracy on benchmarks. And for us, this was much lower. Even though all the bugs that we put into glitchbench were reported by human testers. Okay, so these are all confirmed by humans that they are actually bugs and that they are actually problems in the game. So if you work with LLMs, give it a try, especially if you fine-tune them. Like I said, it's available at the website. It's a Hugging Face data set, so you can run it as an actual benchmark without leakage of the data. All the data in glitchbench comes from short videos, so there's actually not an image and text description available on the web. So there should not be any data leakage. Okay, so looking back, are we there yet? Can foundation models reliably detect visual bugs? Not completely yet, but the future is very bright for visual quality assurance. It really looks super promising, and as these models get better and better and we're able to fine-tune and get more data, then we can really have a really nice performing model. So to summarize my talk, in my lab we look at whether foundation models can help us to detect bugs in video games. So I showed you that current foundation models can already do a quite reasonable job at this problem. And we're not completely there yet, but it looks really promising, and I expect to see lots of progress in the next few years there. So if you have questions, I'll be happy to answer them during the discussion, or feel free to reach out to me. I'll be here for the whole rest of the day. Feel free to reach out on email, have a look at our lab website. Thank you very much.
Thank you very much, Cor-Paul.